All right, welcome everyone. If you're staring down the barrel of a massive chemistry exam and feeling totally overwhelmed by the periodic table, you are in exactly the right place. Consider this explainer your ultimate high-yield study guide. Today, we're not just going to sit here memorizing dry facts. We're actually going to master the underlying architecture of matter. By the end of this, you'll be able to predict the properties of elements you haven't even studied yet.
So here's our game plan. We'll start with the periodic blueprint, then we'll unlock the core mechanism. From there, we'll use that to define the key chemical trends, tackle those tricky high-yield exam exceptions, and finally tie it all together in the ultimate synthesis, a nice logical checklist to get you perfectly exam ready.
Kicking things off with Part 1, the periodic blueprint, organizing the elements.
To really get why this blueprint is so brilliant, we kind of have to appreciate the sheer chaos chemists were dealing with back in the day. Order did not happen overnight. In 1829, Dobereiner tried grouping elements into triads based on weight. By 1865, Newlands noticed repeating patterns, octaves, basically like a musical scale. Then in 1869, Mendeleev revolutionized the whole game. He organized by atomic weight, but had the foresight to leave strategic gaps. Finally, in 1913, Moseley came along and proved with X-ray spectra that atomic number, not mass, is the true fundamental property.
And honestly, Mendeleev's framework survived for one huge reason. He didn't just organize what they already knew, he successfully predicted the unknown. Think about his 1869 prediction for what he called Eka aluminum. He literally guessed a weight of 68 and a density of 5.9. Years later, gallium is discovered out in the wild, atomic weight 70, density 5.94. Spot on. His architecture was so incredibly powerful that it worked as a predictive tool, not just a static list. And that is exactly how you need to treat it on your exam.
Moving right along into Section 2, the core mechanism, which is all about effective nuclear charge.
Listen, if you take literally just one thing away from this explainer, make it this next concept. It is your absolute cheat code. It all boils down to an atomic tug of war. Pull versus distance. Every single periodic trend comes down to this battle. You have the positively charged nucleus exerting a pull on the electrons. That's your effective nuclear charge, or ZEF. But the inner core electrons are pushing back, shielding those outer electrons. As you move across a period from left to right, the nuclear charge goes up, while the shielding stays the exact same. So the nucleus wins. It pulls everything tighter. But as you go down a group, you're adding whole new quantum levels. So distance wins. Master that tug of war, and you've basically mastered the entire table.
Okay, Section 3. Mapping out those key chemical trends.
Let's put that pull versus distance master key to work. We'll start with the most visual, intuitive trend out there, atomic radius. If you get asked to define this on your test, it's just the physical distance from the center of the nucleus to the outermost electron shell. Think of it as the literal size or the footprint of the atom.
Now watch how this atomic breathing actually plays out. Going across period 2 from lithium to fluorine, the atoms physically shrink. Why? Because the nucleus is packing in more protons, pulling that same outer shell in tighter and tighter. But if you look down group 1, from lithium to cesium, they get absolutely massive because distance wins every time a new shell is added. Oh, and a quick high-yield tip for the exam, the isoelectronic species rule. For ions that have the exact same electron count, the one with the highest positive nuclear charge, like magnesium 2+, pulls those electrons the tightest, making it the smallest. Our next core definition is ionization enthalpy. Sounds complicated, but it's really just the precise energy required to remove an electron from an isolated gaseous atom. I want you to think of this as the literal cost of extraction. You are paying an energy toll to rip an electron away from the nucleus's grip.
And since we're talking about an extraction cost, it perfectly mirrors our tug of war. Check out the jagged peaks on this data. Across a period, as that nucleus pulls tighter, the cost of extraction skyrockets, which is exactly why the noble gases sit right at the peaks. Conversely, down a group, those outer electrons are so far away from the center that they're basically unprotected, making them way easier and cheaper to steal. Also, remember this for your test. Successive extractions always cost more. Going back in for a second electron means you're fighting an even stronger electrostatic grip.
All right, definition number 3, electronegativity. Now watch out here, because unlike enthalpy, which is a measurable energy, electronegativity is purely a qualitative scale. It describes the ability of an atom in a compound to greedily attract shared electrons toward itself.
See that dark red corner where the highest electronegativity lives? Fluorine is the absolute king here. Linus Pauling actually assigned it the maximum value of 4.0 on a scale.
Because it's so small and has such a high effective nuclear charge, it hoards shared electrons more aggressively than any other element. Across a period it goes up, down a group it goes down. Once again, it all just comes back to pull versus distance.
Which brings us to Section 4, Exam Exceptions. What happens when those rules break? Because let's be real, your professors aren't just going to test you on the neat, tidy rules. They absolutely love to test the anomalies. When the trends we just established suddenly glitch, that is the exact moment where the difference between an average grade and a top score is decided. You have to know why the rules break.
There are two classic trick questions for the second period when it comes to ionization enthalpy, and you definitely need to memorize these. Exception 1 is beryllium versus boron, which comes down to the penetration effect. Exception 2 is nitrogen versus oxygen, caused by the pairing-repulsion effect. Let's break down the actual mechanics of what's happening.
Looking at the orbital diagrams, these quantum glitches become super obvious. Normally, ionization energy should just increase straight across a period, right? But beryllium has a completely full 2s orbital, which actually penetrates closer to the nucleus. That makes it significantly harder to remove than boron's lone 2p electron. Then, look at nitrogen. It has exactly one electron in each 2p orbital. That's a very stable, perfectly half-filled arrangement. Oxygen, sitting right next door, actually forces two electrons to share a single 2p orbital. That creates electron-electron repulsion, which ironically makes oxygen's extra electron surprisingly easier to remove than nitrogen's.
All right, home stretch. Section 5, the ultimate synthesis. Tying it all together.
We've spent a lot of time zoomed in on invisible quantum mechanics. Now let's zoom out and look at how this manifests as macroscopic reality on your exam. The chemical consequences are pretty extreme. Over on the far left, you get maximum reactivity through electron loss, forming cations. On the far right, the halogens give you maximum reactivity through electron gain. And check out the oxide spectrum. Elements on the far left form basic oxides like sodium oxide. Elements right in the middle form amphoteric oxides, and then the nonmetals way over on the far right form highly acidic oxides like dichlorine heptoxide. The quantum rules are quite literally dictating the macroscopic behavior. And here we go, your ultimate exam cheat sheet, all mapped out. You really don't need to memorize 100 isolated facts. Atomic radius, ionization enthalpy, electron gain enthalpy, electronegativity, and metallic character. Every single one of these trends, whether you're moving across a period or dropping down a group, traces back to that exact same core reason we started with, distance versus nuclear pull. It's an incredibly elegant system when you think about it.
So, as you gear up for test day, I want to leave you with this question. Are you going to rely on stressful rote memorization, just hoping you don't blank out on a flashcard? Or are you going to use this master key, distance versus pull, to confidently predict the properties of literally any element in the universe? Trust the underlying mechanics, study this framework, and you are going to absolutely crush this exam. Good luck.